Now we're in section 4.2, divisibility in f adjoined x. So again, as I mentioned before in the last video, pay very close attention to the pattern that you have in chapter 1 and 2. Again, where most people will mess up modern algebra is they didn't catch the pattern in chapter 1 and 2, so they've been lost the whole time and they'll never catch the pattern again. So it's the same pattern. Look for those patterns here. So, definition. Let f be a field as a of x and b of x are polynomials in f adjoined x, with b of x non-zero, a non-zero polynomial. We say that b of x divides a of x if there exists a polynomial u of x, element of f adjoined x, and that's how you would write it up. If there exists a polynomial u of x, element of f adjoined x, such that a of x is equal to b of x times u of x. Now look at the pattern as compared to the wonderful world of integers. It's the same, but don't be caught cold on calling it an integer. It's not an integer. It's got to be a polynomial. That's what the elements are called in the polynomial rings. It's a polynomial element of, and you have to declare this, f, which is whatever arbitrary field we're giving you, adjoined x. This is the polynomial ring notation. So it's the same thing as what we've had before. So, continuing on. Theorem 4.7 says this. Let f be a field and a of x and b of x elements of f adjoined x with b of x not zero. 1. If b of x divides a of x, then c times b of x divides a of x for each non-zero c in f. When you're playing around with fields, a field adjoined x, even though that b of x divides a of x, you can throw any kind of constant on top of this times this polynomial that divides, and it's still going to divide because of that idea of the being units. C is going to be a unit because C is non-zero, so you can still divide it. And remember, the coefficients are coming from fields, and all non-zero elements of a field are units. So even though b of x divides a of x, any kind of constant times b of x, as long as that constant is not zero, will also divide a of x. That's what part 1 says. Part 2 says this. Every divisor of a of x has a degree that is less than or equal to the degree of a of x. Now that's another big part of that division algorithm that we went over last time, is that for you to be able to divide, you got to be a less degree. This is how you compare polynomials. You look at the degree. So the one with the smaller degree will kind of divide it into the bigger degree. So every divisor of a of x has a degree less than or equal to the actual degree of a of x. Another definition, an important definition, is this. A monic polynomial is a polynomial with a leading coefficient of 1 in f. Again, we're talking about f adjoined x. So we're going to start disseminating the different types of polynomials. So how do we make these polynomials unique, since every constant times a polynomial will also divide? Well, if you get rid of the leading coefficient and make him just a 1, then that will make the polynomial unique. So this monic polynomial is how we're going to put the uniqueness in terms of these polynomials. So a monic polynomial is a polynomial with a leading coefficient of 1 inside of whatever field you're adjoining x to. Another definition. An element A in a ring R is said to be an associate to B, element of R, if there exists a unit in R called U, such that A is equal to B times U. So we're going to sit there and talk about the idea of associates. The associates is the relationship between elements. So if I've got two elements, they're not equal to each other. But if these two elements are such that if I take one element, multiply it by a unit, an invertible element, it's equal to the other guy, then the A and B may not be equal to each other, but we're going to call these guys associates. So they're almost equal to each other. They differ by just the idea of multiplying by a unit. Definition. And don't be surprised by this. Again, look for patterns. Definition. Let F be a field and A of x and B of x be elements of F adjoined x, not both 0. The greatest common divisor of A of x and B of x, yeah, we got it denoted, GCD of A of x comma B of x, is the monic polynomial D of x of highest degree that divides both A of x and B of x. So that's how we're going to make the GCD unique. We're going to make that leading coefficient of the greatest common divisor a 1, and that makes the polynomial unique. So this GCD is going to be a unique polynomial here because it's going to have a leading coefficient of 1. And this polynomial will divide both A of x and B of x, and this polynomial that's the GCD has to be of highest degree. That makes it the greatest. So, in other words, catch a pattern. D of x is equal to the GCD of A of x and B of x, provided D of x is monic, a monic polynomial, and I'll use my little shorthand notation here, D of x divides A of x, and D of x divides B of x. And number 2, if C of x divides A of x, and C of x divides B of x, then the degree of C of x has got to be less than or equal to the degree of D of x. That right there is making D of x the GCD because it's the biggest polynomial that does it. So, biggest by definition of degree. Now, if you look at this definition, it's been changed slightly, but it follows directly from corollary, actually the definition of GCD from when we were playing around with integers. Except we got to put a few little things in there. The idea of monic, and when you compare polynomials, you have to compare them by degree. Other than that, this is exactly the same. So this is a very important comparison between the two, and it shouldn't come as a surprise. But remember, to have a GCD, you got to make sure the polynomial is monic. The leading coefficient is going to be 1. And if it's not 1, just multiply by the inverse of whatever that leading coefficient is, because remember, you're an element of F adjoined x because you have a field, so every non-zero element is going to have a unit. But that constant unit that you multiply the entire polynomial through by that, you're going to make the polynomial monic, and that will make it a GCD. So if we got the definition is that close, take a wild guess of what the next theorem is going to be. And catch your patterns here. Theorem 4.8. This is another one of those theorems that you're going to look at and go, I'm going to use him a lot. Theorem 4.8 says this: let F be a field and A of x and B of x be elements of F adjoined x, not both 0. If D of x is equal to the GCD of A of x and B of x, then there exist, not necessarily unique, polynomials U of x and V of x, element of F adjoined x, such that D of x is equal to A of x times U of x plus B of x times V of x. If you've got a GCD, you can write yourself a big equation. What is the difference between Theorem 4.8 and our old Theorem 1.2? I put an X on all the letters and declared them to be polynomials. It's the exact same thing. So these will be polynomials instead of, quote, integers. But it's the exact same thing. If I got GCDs, I can write myself an equation. There exist, not necessarily unique, U of x and V of x polynomials in F adjoined x, so I can write an equation. And similarly, we have our corollary 4.9, which kind of corresponds to corollary 1.3 with integers. Take a look. If let F be a field and A of x and B of x be elements of F adjoined x, once again, not both 0. A monic polynomial D of x, element of F adjoined x, is the greatest common divisor of A of x and B of x, d of x equals the GCD of a of x and b of x. Well, first it's got to be monic, okay? If and only if d of x satisfies the following conditions. And there's two conditions. I'll use a little shorthand notation here. D of x divides a of x and d of x divides b of x. That's that definition of divides concept of GCD. It's the D part. It's the divisors. So d of x divides a of x and d of x divides b of x. Part 2 gives me the greatest. If c of x divides a of x and c of x divides b of x, a completely different polynomial divides a of x and the same polynomial divides b of x, then c of x has to divide d of x. It will divide the actual GCD because the GCD will be the biggest polynomial. And a little side note, it's a definition here, but it's a definition you've seen before. Polynomials f of x and g of x and f adjoint x are said to be relatively prime if the GCD of f of x and g of x is equal to 1, and with a little subscript f, in whatever field you're playing with, the 1 in the field of elements that you play with. One's going to look kind of different depending on the ring you have. So you got it. Same deal. So you know Theorem 4.8 says this. It's a one-way implication. If you have a GCD of a and b equals d of x, you can get an equation out of it. If you got the GCD, there exists polynomials u of x and v of x and f adjoint x such that you have an equation. You can't go the other way. Just because you got an equation doesn't make what it's equal to the GCD. But if these two polynomials, a of x and b of x, are relatively prime, then you can go both ways, because 1 in f is going to be the smallest monic polynomial you got, because the leading coefficient is 1 because it's equal to 1. So if you got the equation equal to 1, then you can actually go back the other way and say the GCD of a of x and b of x actually equals 1. They're relatively prime to one another. And I'm going to call that Theorem 4.8b, just like we did with Theorem 1.2b. And when you got relatively prime, you can actually go both ways. So if I want to prove that somebody is relatively prime, I want to set the equation equal to 1. It only works with 1 because 1 is the smallest positive polynomial that is monic. So these guys are very, very similar. How similar are they? Well, let's take a look. Here is a problem very similar to whatever kind of homework problems I give you guys on this material. Again, catch a pattern, and the pattern is going to be chapter 1 and 2 again. Theorem 4.10 says this: let f be a field, and a of x, b of x, and c of x be elements in f adjoint x. These are polynomials in f adjoint x. If a of x divides b of x times c of x, and the GCD of a of x and b of x is equal to 1, they're relatively prime, then a of x divides c of x. Alright, let's prove it. So I'm given that a of x divides b of x times c of x, and I'm also given that the GCD of a of x and b of x is equal to 1. A of x and b of x are relatively prime. I want to show a of x divides c of x. To be able to show a of x divides c of x, I want to write an equation which c of x equals, and be able to, quote, factor out an a of x. Remember, these are polynomials, not integers, but the pattern will be the same. So when you start your proof, you always start out with the givens. So given a of x divides b of x times c of x. By definition of divides, there exists a polynomial w of x, element of f adjoint x. You have to kind of describe to me that yes, this guy is in my ring, the polynomial ring, such that now if a of x divides b of x times c of x, who's bigger? B of x times c of x. Such that b of x times c of x would be equal to a of x times w of x. And also given the GCD of A of x and B of x is equal to 1 in your field. Well, the only one thing I can do with GCDs of two polynomials equals 1, and that is Theorem 4.8. And you can quote it as Theorem 4.8 or Theorem 4.8b. By Theorem 4.8, and I'll put a little b in parentheses because you could use either one, there exists polynomials. I use my favorite guys, u of x and v of x, elements of f adjoined x, such that we get a nice big equation. A of x times u of x plus b of x times v of x is equal to 1. Now, I want to show that A divides C of x. A of x divides C of x. Which means I want an equation with C of x equals, and I need a big equation with C of x equals. How do I get a big equation with C of x equals? I have here, I got B times C is equal to somebody, but I don't have anything about C of x equals. Remember, you've got an equation equal to 1. You can turn 1 into any equation equal to whoever you want to by just multiplying the right guy on both sides. And that's going to be my trick. As A of x times u of x plus b of x times v of x is equal to 1 and f, then C of x times A of x times u of x plus b of x times v of x is equal to C of x times 1 in f by multiplying by C of x on both sides. So I'm going to do this indenting type of thing here because I'm going to manipulate my equations here. Okay? Thus, C of x times A of x times u of x plus C of x times b of x times v of x is equal to C of x by distribution. I distributed C of x. Remember, we got f adjoined x. That's an integral domain. F's a field, but f adjoined x, when you attach that x on there, makes it an integral domain. It's not going to be a field anymore because x is in your polynomial, but 1 over x is not. And because of that, we have f adjoined x is going to actually be an integral domain. F's a field, but once you attach that to an x, it makes it an integral domain. But integral domains have distributive property. Hence, C of x times A of x times u of x plus, I got C of x times b of x. But we know that b of x times C of x is equal to A of x times w of x. So that would be replacing b of x times C of x times b of x with A of x times w of x times v of x equals C of x by substitution, actually. Substitution. And that would have been fine, but it may bother some people that, hey, you replaced b of x times C of x with something with is C of x times b of x. But remember, f adjoined x is an integral domain, which it means it's a commutative ring with identity. So if you want to say and commutativity, that's fine with me too. But substitution would just do it. But notice what you have in common here. I got A of x on both terms. This gives us A of x times C of x times u of x plus w of x times v of x is equal to C of x by factoring. And remember, factoring is the distributive property in reverse. You could just say distribution if you want to. So I've got A of x times somebody is equal to C of x. But that somebody has to be not integers anymore. It's got to be a polynomial. So why is this guy a polynomial? Well, since C of x, U of x, W of x, and V of x are polynomials in f adjoint x, then C of x times U of x plus W of x times V of x is a polynomial in f adjoint x because f adjoint x, yes, you can say is a ring, but I got it better than that, is an integral domain. I'll put ring in parentheses there. It's really because it's a ring, but the fact of the matter is it's because the sum and products of elements in a ring are still going to be in a ring, but f being a field adjoint x makes the polynomial ring an integral domain. So it's got even more properties than just a basic ring, but we're using the basic ring properties here. Therefore, by definition of divides, A of x divides C of x, which is what we wanted to prove. And I'm done. Again, if you go back and look at your other material, you will notice that this question was very similar to integer questions that I've given you before from your textbook, as well as some of those problems from homework 1, 2, and 3. So again, if you go back and look at these things, you get to see the idea that, look, all we're doing is change the world of integers to the world of polynomials, but it's the same. So if I was a betting kind of fella, I bet that if I go back and take all those theorems that we've proven with integers, change the word integer, stick an x on all those little guys and make them polynomials, I bet they're going to do the same thing. Because a lot of folks ask me, you know, Dr. Taylor, how did you get a doctorate degree? What do you got to do to get a doctorate degree in mathematics? To get a doctorate degree in mathematics, what you have to do is you've got to come up with your own theorem. It's called a dissertation, but math is much more hardcore than any of the other sciences. You have to come up with something that no one else has ever come up with before. You've got to create your own theorem. And typically, when you create one theorem, you catch a pattern in a few more theorems, and corollaries and lemmas tend to show up as well, and you put them together in a book and you call that your dissertation. The trick of doing that is, number one, you've got to have a great advisor. The other trick is this: catch a pattern. When you're working in a world that you've never played with before, and you catch the pattern that, hey, this world is different and new, but it seems to behave like something else that we have studied before. So you take those theorems and that you've studied before that are for something else that this thing seems to be very similar to, and you kind of transpose them over and putting in the concepts in the world that no one's seen before, and hopefully the patterns will be the same, and you can write those guys up as something completely different and make new theorems out of it and stuff. And that's why you get to call me Dr. Taylor. So there you go. So, and anybody who's got their doctorate degree in mathematics, they have gone through this dissertation aspect of creating new theorems from material that has they've just discovered and stuff like that. So that you guys know what you guys are hopefully going to go for when you go to graduate school. So hope this has been helpful. I'll see you on the next video.